All right, well, thank you. First of all, I'd like to thank the organizers for all the hard work putting this together. It's been a great meeting so far. And it's also a pleasure to be back as a lecturer. I came to the very first CIDER as a postdoc who just got a PhD 12 years ago. Gives you my age. And it has been great. So we had a lot of discussions. One thing that I still vividly remember is that as a student or the young participants, we had to come up with 10 or 12 unusual questions. And one of those was, what's the color of the mantle? We actually spent quite a bit of time discussing that, and I still think about it once in a while. Of course, when I watch the movie Core, that's this answer right there. And it also, as you'll do, we broke into different groups. We did a little bit of a research. Back that time, we just had the discovery of post-perovskite. It has been very exciting. And the group that was looking at the post-perovskite followed up with the EOS article. So hopefully you'll get something very useful out of this meeting as well. And I also made a lot of connections at this meeting. So last week I was in Japan collaborating with a mineral physicist who I first met for the first time at CIDER as postdocs, and we still work together. So I think you'll find this useful. So today I was asked to talk about the normal modes. And I thought about it, looking at the lectures on Monday and Tuesday. I thought about, OK, I could start with the momentum equation, do the boundary conditions, and so on and so forth. The problem is I'm not very good at explaining equations. I could spend the entire hour and a half talking about the summation notations, and I don't think you want to hear about that. So I'm not going to take that approach. I'm going to give you a lot of hand-waving arguments as to what we observe and what sort of things can be done with normal modes. But feel free to ask questions. I have some slides prepared for those hardcore theorists so that I can show you some equations if you are interested in that sort of thing. And please do interrupt and ask questions. I'm sure in the last 2 days you've been listening to all these talks and someone asks a question and you'll be nodding your head that, yes, that's something I wanted to know. And so if you have a question, your neighbors will probably have similar questions. So just ask the question, and if it's a short one, you don't want to wait for the microphone, I'll just repeat the question, so just shout out. Okay? So as the outline for my talk, I'm going to introduce you why we want to do normal modes and what they are. And we are basically going to look at that from the perspective of the thesis of this workshop, which is the flow in the mantle. So my focus is going to be more on the density rather than P waves and shear wave speeds that we've been talking about. I'll focus on the 1D model that comes out. Well, not necessarily just from the normal modes, from all the seismological constraints, and I'm going to focus on PREM. And there, I'd like to spend a little bit of time talking about the Bullen's parameter that Quentin mentioned yesterday a little bit. And that's because there are certain issues with PREM. And then I'm going to go in and explain how the normal modes can be used to constrain three-dimensional structure. And I'll also spend a little bit of time describing what are the advantages and disadvantages. There are certain problems of using normal modes, but there are certain advantages. And then if I have time, I'll get into attenuation. But again, I prepared it so that I'll be running out of time, so I might not going to get into that. All right? So Steve Grant gave us a very nice introduction yesterday about seismology. So what I'm going to do is I'm going to pick up from where he left. So he left by showing the wave propagation through the Earth. So I'm going to do the same thing. Up here, I have an Earth, the surface view. And here is the cross-section of the Earth. I just cut it in half. What I'm going to have is an earthquake in Alaska, a Denali earthquake. And I'm going to observe the wave propagation through the Earth in this side and along the surface on this side. And as I go along, what's going to happen is I have these stations, College, Alaska, Pinion Flat, and so on and so forth. And those stations will be recording the ground motion, which will be shown on the top panel. Okay? So when the earthquake happens, that would emit seismic waves. And as Steve showed, you have the P waves in red, S waves in cyan color in this case. And you have a lot of complexities. And these waves are arriving at various stations, creating blips that we can observe. So what we typically do as seismologists is to try to find out, OK, here are our observations, and what can we do with them, right? So we have a lot of body wave data. the travel times of S and P waves, which, since we know how long it took them to arrive and when they started and the distance of the source to the station, we can convert those to seismic wave speeds. So the one-dimensional model PREM has a lot of that information in there. So the preliminary reference Earth model from 1981, it is showing the model from the surface of the Earth to the center of the Earth. And on this axis, I'm showing the wave speed, kilometers per second. That corresponds to P wave and S wave profiles. But I'm also plotting the density profile here in green, and that scale is up here in grams per cubic centimeters. Now, this is a one-dimensional model in the sense that it only depends on the depth. There is no lateral variations. The Earth is covered with 3 kilometers of water, which we know is not true, but we still work with that because that is a very good model. This is a very good model in explaining seismic observations. It is an average Earth structure. It tries to explain the average observations as much as possible. And the way this was constructed was using mostly the seismic data. So the first input were those P wave and S wave travel times. We have a lot of those observations. Steve showed a very nice picture of millions of observations in there. This particular model had about 2 million P travel times and about 250,000 S travel times. Okay? So that's where we can start. Now, if we go back to the seismic wave speed definitions, Steve Grant derived it using a wave equation and so on and so forth. The body wave data are giving you the S and P wave speeds. So what are they? Just going to remind you. S wave speed is simply square root of mu, which is the rigidity or shear modulus, divided by density. Fairly simple. That's one wave type. The compressional wave type P wave speed is very similar in this as to this form, square root of kappa, which is the bulk modulus or incompressibility, plus 4/3 of the shear modulus, all divided by density. Okay? Now there is a problem here. How many equations do we have? This isn't. I see a microwave. This might be confusing because the seismologist has a tendency of calling this S wave speed and P wave speed as velocities, but they actually are scalar parameters. So there are no vectors in here. Okay? So there are 2 equations. How many unknowns do we have? 3. Right? So yes, we can measure the S wave speed, P wave speed, but when we want to come to density, that's not straightforward. Steve Grant showed you a rare case where we could use the body wave to get density. That's when we have the reflections from discontinuities. But then we have to be looking for reflections and their amplitude of the reflected waves, and that amplitude in seismology is something that is very difficult to do very accurately. So, and the other problem is that density is associated with the density contrast at the boundary. So if you're interested in the volumetric density variations, you don't really have a lot to go with, right? We could do S waves very well and P waves very well, but not necessarily density with body waves. But why are we interested in density? Why do we want to look at density structure? Okay? Well, one reason is if you want to start to talk to other people, not just seismologists, mineral physicists would be looking at density. It's something that they can easily constrain, and I get a question, so which model should I use for density? Right? So this, if I have density from some constraint of density, it would make me easier. It would give me some tool to talk to mineral physicists. It would also be a good tool to understand if you're interested in dynamics of the Earth. To the first order, Earth dynamics is driven by density buoyancy, driving force. So if you're interested in various observations, the gravity field, the geoid, how the plate works, the plate motion, dynamic topography, all those things are associated with dynamics of the Earth interior. So if you want to know that, you'd probably want to know what sort of driving forces you have, in other words, density variations inside the Earth. The way these are done is typically through flow calculations, which has typically two things as input. One is the density variation, three-dimensional density inside the Earth, as well as viscosity variations. Okay? So we like to get to the density. Seismology has a hard time when we come to the body waves, but this is exactly the same figure as Steve Rand showed you. There are different flavors of seismic data. Right? He focused on the body waves. This is as a function of period and as function of frequency. So this is where seismology, the typical global seismology, is sitting in this frequency range from about 0.1 to thousands of periods, seconds. Okay? In terms of frequency, we are looking at tens of hertz to millihertz. Now, in terms of scale, the sound we hear, the sound you're hearing, is sitting on this range, so it's very high frequency. On the low frequency end, we could have crustal deformation, which is of the order of centimeters per year. And we also have some intermediate phenomena like Earth tide, which is daily, semi-diurnal, and so on and so forth. The topic of today, or my talk today, is the normal models. So they are sitting here at the lowest end of seismic spectrum. And so sometimes this is referred to as low-frequency seismology. Now, normal models, what they are is they are simply ringing off the Earth. If you have a large earthquake, it's similar to hitting a bell. And so think of Earth as a bell and earthquake as the force that hits it. When you hit the bell, it would start to ring. And you can hear the sound, a single sound, and that will be your characteristic frequency. When I hit the Earth with big earthquake, I don't do it, the Earth does it on its own. And if you take the long time series and Fourier transform it, in other words, trying to find these sounds, different frequencies of the Earth's sound, I would get something like this. So this is from a vertical recording, so the vertical ground motion from 2004 Sumatran earthquake. It was somewhere between magnitude 9.15 and magnitude 9.3. This is as a function of frequency going from 0.2 millihertz, not just hertz, millihertz, to 1.2 millihertz. And I see these nice peaks. These have the periods of roughly about 83 minutes and 14 minutes. So remember, body waves are of the order of 1 second period. We are talking about something that is very, very low frequency or very long period phenomena. And you see these nice peaks corresponding to different sounds of the Earth. Just imagine dropping a piano and you'll hear different sounds, but they would have characteristic frequencies. They have different tones of them. And that's what these are. You're hearing different tones of the Earth. Okay? Now, what are these tones, or how are they periodic? Well, if you look at this particular mode, 0S0, this nice sharp peak here, it corresponds to the Earth's ground motion, that is Earth breathing in and breathing out and rotating or oscillating between those two with about 21 minutes of period. So over 21 minutes, the Earth inflates and deflates. Okay, so the Earth breathes in and out. We can relax. Right? Now, that's not all. We have other modes, so let's take a look at another one, 0S2. This is the gravest mode that we have, in other words, longest period mode we have. And this mode has a different behavior. It oscillates between being oblate and prolate over a time or period of almost an hour. So it rotates between squashed and pulled.
Do you mean the seconds underneath the minutes? Because you put like 497 hours.
I will get back to that later. So the question was, what was the 4,000 whatever hours? And
97 hours.
yeah, I'll get back to that later. It's actually the decay of the mode. So this 0S2 is flattened and pulled, and it oscillates between two shapes over about an hour. I can assure you, This is highly exaggerated. If this happened, we won't be sitting here. The 0S0 mode for the 2004 Sumatra had an amplitude of peak to peak of plus or minus 5 centimeters, so it's tiny, and since it happens over a long time, we won't feel it. If this happened, we will be feeling that. Now, this isn't all. You could have some other modes which would have more complicated sort of deformation style, and so you're basically working the Earth as the entire entity. Right? You're working not just, you don't have a source and receiver and looking at the ray path. You're actually getting the entire Earth to move.
Does the Earth have a divide temperature? Is there a maximum earthquake that excites all of the modes?
That's a great question. So if we look at something a little bit smaller, magnitude 8.4, we still consider it to be a very large earthquake. But because that doesn't have enough energy, it won't be able to associate some of the gravest modes. You can see that there's this 0S0 and 0S5 peaks. So some of the modes can be excited. It also depends upon the depth of the source and so on and so forth. But you definitely need a large earthquake in order to get the Earth into this sort of motion. Any other questions?
Of those two events that you've just shown?
The radiation pattern, they are both a thrust earthquake, similar depth. So the radiation patterns are relatively similar, although because the locations are slightly different, there is a bit of difference. But this isn't due to the fact that it's a radiation pattern. Any other questions?
The relative amplitude of two modes really represent how strong is it on the Earth?
Between these two earthquakes?
Yeah. No, for example, if we took the OSO modes and the OS2 modes, and the relative amplitude, does it correspond to the relative amplitude we observe on the Earth?
It does correspond to the what we observe on the Earth. Right? But the amplitude depends upon the source mechanism and things like that, and also where the station is. So at this station, the amplitude that you observed corresponds to these relative amplitudes. And if I have time at the end, if I can get into attenuation, I'll show you how the amplitude changes as a function of time. Anyone else? Okay, so that's the vertical motion, or something that has to do with volumetric change. Now, if you're interested in three-dimensional motion, you actually need one another type of mode, which is called toroidal mode. So this involves volumetric change, right? You see the Earth being deformed, has a different shape, and so on and so forth. The other type is called toroidal mode that has to do with purely shear motion or horizontal motion. So if I now look at the horizontal component, east component from the same two earthquakes, from the Sumatran earthquake, we see more of the peaks. And now, in addition to these S peaks, which are corresponding to those spheroidal volumetric change modes, I have the T modes, which correspond to the toroidal modes. So if I look at the 0T2 mode, the toroidal mode sitting down here, the motion it has is it has the hemispheric shearing. So when the northern hemisphere goes eastward, southern hemisphere goes westward, and it goes the other way. The northern hemisphere goes westward, southern hemisphere goes eastward, and it oscillates between those two types of motion, two types of rotation. And it has the period of about 44 minutes. So you know what's coming, right? The Earth gets sheared. Now, this is fairly simple sort of motion. If you want to get something more exotic, you can have the Earth looking like that. Again, this is highly exaggerated. Okay? Any questions? So what can we do with this? It's fun to look at these movies, but there is something useful that you can do with MOS. So what we have is these observations. From these observations, we can infer characteristic frequency of different sounds. What frequency are each of the piano sounds? So we have 0S2 that would give you certain period or frequency, so about a 51 minutes. And that characteristic frequency is associated with the Earth's internal structure. So imagine hitting a wooden bell and a metal bell. The sound would be different because the material is different. What's happening here is these characteristic frequencies, the sound you hear from the wood versus the metal bell, is going to tell us about the Earth's internal structure. And the modes are sampling the interior in various ways, and that's how we can infer what's down there as a function of depth. So here is one illustration of what we call eigenfunction of a mode 12S2. And it has two eigenfunctions associated with the more or less vertical motion and horizontal motion. And this mode is sensitive to structure in the inner core, structure in the outer core, and structure in the mantle. Some modes are not necessarily sensitive to every single layer. So by collecting all the mode observations, we can start to infer what's there underneath at the various depths. So remember, the normal modes are the entire Earth motion. This gives us additional advantage. In other words, the fact that you have the Earth moving like this means that the gravitational restoring force is going to be important. If you deform the Earth, there will be some sort of gravitational restoring force that's going to try to push it back to its original position. Gravity is associated with density. In other words, normal mode data would give you variations or constraints on P and S wave speeds, just like the body waves in a sense, but we can also get an understanding of what's happening in terms of density because we have this sort of gravitational restoring force in our equation. So coming back to PREM, we had a lot of the body wave observations, P and S travel times. In addition to that, notice that PREM has a density profile. They included about 900 characteristic frequencies of the modes. So they observed various modes, sounds of the Earth, measured the frequencies, and included in this. Now, it turns out they are not good enough to do the density as detailed as you can see it in PREM. So they actually had to complement this with various data sets. One thing they wanted to satisfy are the radius and mass of the Earth. We know those very precisely. We might as well throw that in, as well as moment of inertia. So these contribute to density constraint that is in the PREM. That was not quite good, strong enough constraints to give you a more or less unique solution. So they also added another constraint, Adams-Williamson equation. It basically relates seismic wave speed to density variations, and that's how they could make this density variation in a lower mantle. Now, that poses certain problems. So if I look at the change in pressure, I can write it as density times gravitational acceleration times change in radius. That's fairly simple. How much of material do I have? If I assume adiabatic condition, in other words, there is no exchange of heat, and assume homogeneous material. If something is vigorously convecting, we would think it would be mixed very well. So adiabatic means that you just have a parcel of material, you put it up and down without loss of any heat. Okay? If I make those assumptions, I can also write the change in density as a change of pressure in this form. It's simply related to density divided by the bulk modulus or incompressibility that you saw in the P-wave equation. Now, this is also written as phi to the minus 1. Mineral physicists like to call this phi seismic parameter because we can obtain this parameter from seismology. If you take P wave speed, square it, and then take 4/3 of S wave speed squared, you'll end up with this seismic parameter phi. Yesterday's Steve Grant's talk, he referred to this as the bulk sound speed squared. Now, that's all fine. If I take this equation and take this dP definition, bring this down here, and then bring this on the other side, I'll have 1 is equals to minus seismic parameter, because I've moved this to this side, times the density and gravity inverted, because they are going to get down here, times dp by d rho. It's 1 for this particular case. Right, so I'm going to keep with that definition, adiabatic, no exchange of heat, homogeneous composition, so I have that. Now, the Earth isn't necessarily adiabatic. So if I say, okay, let's relax my condition, let's say I'm going to consider anything, not necessarily just adiabatic. That means that in this equation, I have to add heat flux effects. In other words, heat is coming in and out because I've relaxed adiabaticity. I could also relax the homogeneous condition. The Earth interior might not be homogeneous. Then I'll be adding to this equation the effect of heterogeneity. Right? In other words, when I write it in this form, I no longer have a constant 1, but some number, which I don't know, but I'm just going to define it, or someone defined it as Bullen's parameter. Most likely Bullen defined it as the Bullen's parameter, as this expression. Okay. So what does this tell us? Well, if you have a homogeneous material that's convecting, so I'm heating from the bottom, cooling at the top, have a nice thermal convection. In the center where it's well mixed, convecting core, I should expect this condition, adiabatic homogeneous. And I would get an eta Bullen's parameter of 1. On the other hand, at the boundary layers, at the top and the bottom, because we are not quite doing that, we are not vigorously mixing, we should get eta value of less than 1. So the eta values are going to tell us about what sort of things we have. This is going to be one parameter we can look at in order to understand what's going on. When eta is about 1, its homogeneous material with temperature gradient is equals to adiabatic gradient. That happens at the core of vigorous convection. When eta is greater than 1, the material is more compressive than in homogeneous adiabatic conditions. In other words, the density increases more rapidly with depth than if you had adiabatic condition. That might happen if you have a phase change. When eta is less than 1, that means the material is less compressive than in homogeneous adiabatic conditions. In other words, density increases less rapidly with depth. And that might happen at thermal boundary layers. Okay. So the parameter eta is some sort of indicator. We can use it as a convection indicator, assuming that we are dealing with homogeneous material. So in a lower mantle, we would expect something like this. We have a value close to 1 if we have homogeneous, well-convecting material. So let me come back to this well-convecting material, thermal convection case, and look at the eta value. So this is a profile from the top to bottom, so cold to hot, and this is temperature. So you have hot material at the bottom, cold material at the top. You have the thermal boundary layer here, and the bottom thermal boundary layer there. So this is simply the average temperature profile as a function of depth for this sort of thing. So it's hard to see, but there are these thermal boundary layers. Now, at the thermal boundary layer, as I mentioned, the eta should be less than 1. In the middle, where we have, it actually has a little bit of an overshoot, and with the eta greater than 1 at the top and just below and above the thermal boundary layer. But in the middle, where we should have good mixing, the eta value should be 1. Now, lower mantle, we would expect it to be convecting vigorously. So we would like to find something, eta variation that starts out with being less than 1, slightly greater than 1, comes down to 1, and then goes up and down. So let's test that. We have PREM. Now, the eta definition says that we need the seismic parameter. We can get that from the P wave speed and S wave speed. We have a density that's in here. Because we have density profile, we can also calculate the gravitational acceleration as a function of depth, as well as how much density is varying as a function of radius. So if I do that for PREM, this is the Bullen's parameter eta as a function of depth in the lower mantle. So I start at 660 or so down to 2,890. The red line is the eta being 1. Okay? So instead of having a value close to 1, it's actually below 1. In other words, there's some problem here. Right? The lower mantle doesn't seem to be convecting. The problem becomes a little bit worse because we know that the mantle isn't simply thermal convection. So if I come back to this thermal convection case and now consider what happens. If I consider internal heating, and let's just get rid of the thermal driving force. In other words, I'm going to turn off heat here and cooling there and just consider convection by internal heating. Radiogenic heating. The temperature profile would look like this. In other words, the eta value, in other words, I'm adding heat flux effects into this equation. If I include both the internal heating and in other words, the eta value should be greater than 1. If I bring back the thermal heating, and add to the internal heating, the temperature profile would look like this red line. In other words, the eta is still going to be greater than 1. Okay? So Raymond Johnlos has been working on this in the 80s and 90s, and his suggestion is that in the lower mantle, eta value should be somewhere between 1.02 and 1.07 if the mantle is vigorously convecting.
Yeah, 2 questions. Why does the green curve look the way it does? And is the difference between 0.98 and 1 important?
So the question was, why does the green curve look the way it is? And is this small change from 1 or 0.91 to 0.02 or 1.02 or 1.07 important? The first answer to it is this green curve is simply the temperature profile, and I think they did cool it at the top. And then there was internal heating distribution inside, and that's why it looks the way it looks. Is this difference important? I think it is, because I think the modes might be able to constrain this sort of at this sort of level. At least, well, what happens is I can't do it. So.
Yeah, question here. What do you mean by vigorously convecting lower mantle?
So the question was, what do I mean by vigorously mixing lower mantle? I mean by the fact that you have vigorous enough mixing so that you end up with sort of homogeneous sort of material on average.
Do we know that?
I don't. But if you consider Rayleigh number and such, the Earth should be convecting fairly vigorously. So if I apply that argument to the lower mantle, I could make this sort of argument that if it is vigorously convecting, it should be somewhere around slightly above 1.0.
Couldn't you turn the argument around?
Yeah, I'll just repeat your question, so that's okay.
And say that if PREM shows that
it's not convecting vigorously, well, maybe that tells us something about the Earth.
So the question, I think the initial bit got cut off. If the question is, can't we just turn the problem around and say, okay, if we believe in PREM, it's just telling us that the Earth is not as vigorously convecting as we would expect from the Rayleigh number and such. I agree. That's one way to look at it. The only thing I would be careful with that is that the density constraint is great, and the fact that we have that Adams-Williamson equation that we don't really know if that's completely valid or not. So we could ask this question of, okay, if the PREM isn't quite right, what sort of things should we expect?
Completely, but the Rayleigh number could be quite different for the lower mantle than for the upper mantle, right? Because the Rayleigh number has the viscosity in the denominator,
right? And
if the upper mantle is about 10 to the 20 and the lower mantle is 10 to the 22, it's switched over.
I'll just repeat your question. Yeah. So the comment was that if the Rayleigh number for the lower mantle could be very different because of the viscosity increase of the order of 30 to 100, and then the Rayleigh number might be would be lower, and therefore the convection will be more sluggish. So I'm going through the exercise of what sort of things can we do if we want to satisfy the fact that if you think that the Earth's lower mantle is convecting vigorously, what sort of problems do you run into if you use PREM?
So where did PREM get the density from? I thought they used Adams-Williamson.
Right, so the question was, where did the PREM density come from? The PREM density came from the mode constraint, mass of the Earth, inertia of the Earth, and then the Adams-Williamson equation. So, right, but so you have additional constraints. So eta ends up being a bit different. So this is comparison of various one-dimensional model. Y-axis, again, is Bullen's parameter, and then the depth. PREM is in this black curve, and you see there is a fairly large variation between various one-dimensional seismological models. And that's because the density is hard to constrain. But in this case, what we have is the density gradient as a function of radius. So most of the models that are widely used end up having a value that's less than 1. The two models that you see here that have significantly large eta value greater than 1 are 1066A and B. Those models are earlier versions of one-dimensional models, and they turn out to be the ones that best fit the mode data. Now, whether that has any implications in terms of the eta or not, I'm not quite sure. So what we are ending up with is some problem in the lower mantle. We do have this sort of thing up there, but down there, we're not quite sure what happens with the PREM. So what you can do with modes, and I'm not going to get into in the interest of time, what you can do is you can pose this question slightly differently, and instead of trying to constrain density, you can try to constrain the Bullen's parameter immediately. And if anyone's interested, I'll be more than happy to talk about that. Any questions before I move on to three-dimensional variations? Don't be shy. Okay.
Well, I'll ask a question. If you go back one slide.
You want to see the
One more. So can you summarize what I should take away from this? That we don't know Bullen's parameter, or?
The one point is that the Bullen's parameter is not well constrained from seismology, and most of the time they end up being fairly significantly less than 1 in most models.
Because if I were to take those curves and average them, I get something close to 1. Which?
Well, that's one approach. I don't think a lot of people use 1066A and B anymore. So I think you need to throw these out, and these large variations are just artifacts of the fact that I'm taking derivative with respect to radius. And so if you average this black dotted, black solid, and red, you'll certainly end up with a value less than 1. So can we? It's okay. I'll just repeat your question.
Is this misfitting potentially related to the fact you're using a one-dimensional model?
Is this problem related with the fact that we are concerning one-dimensional model when there are lateral variations? This argument also comes from considering one dimensions, so average model. And the lateral variations in here are of the order of %. So I think that will be relatively small. Although if you want to do this really, really rigorously, I would guess that you would have to consider the fact that there are strong lateral variations around. Barbara?
So, because I haven't checked, but isn't it true that they introduced the Adams-Williamson equation that wasn't included in 1066A and B?
Yes, so after 1066A.
Partly to kind of smooth this out.
Yeah, so after 1066B, they did introduce that Adams-Williamson. So the assumption is not in this blue and green curve, and that might be the reason why it goes way above 1 and it also goes way below 1. So we get to see the daemon once more.
Sarah?
You want to see the daemon, right?
So, I mean, the AK-135 model isn't, that old or bad. Is the upshoot around 1,000 kilometers real?
This red one?
Yeah, I don't know.
It has to do with the way I'm taking the radio derivative.
Okay, so it's probably not real.
Yeah, it's not real. Okay. This bit is not real. Anyone else? Okay. So what else can we do with modes? So I'm coming back to this graph. And if you look carefully, I said each mode has its own characteristic frequency. But if you look very carefully at this, you'll see that there are multiple peaks here, not just one. If I zoom in on this, I actually see 5 peaks. 1, 2, 3, 4, 5. This is a station that is sitting up here with respect to the source there. Now, if I look at another station, a station that is in here, the splitting, or this multiple peak, looks slightly different. Now, this splitting of a mode is associated with the fact that Earth isn't stationary, Earth is rotating, Earth isn't perfect sphere, in other words, Earth is slightly elliptical, and the Earth has lateral variations. So the splitting comes from rotation, ellipticity, lateral variation, anisotropy, whatever is not in the calculation of the single peak. And these 3 are the most significant ones. Now, rotation and ellipticity, I know exactly, right? I know how fast Earth is rotating. I know how much the Earth is flattened at the poles. So I can correct for these effects. In other words, whatever I'm left with in terms of the splitting would be the effect coming from lateral variations. So I can use that information to infer lateral variation inside. Note that the splitting looks very different in this direction and that direction. So the splitting is location dependent. So what we do is we take this sort of information and convert that into a splitting map or a splitting function, and it would look like this. The way to interpret this is that at a given point, this is how the mode is looking beneath at that point and saying, okay, here is the integrated information of all the lateral variations. What do I mean by that? Consider this to be the map. And the map is created by the radial averaging or integration from the center of the Earth to the surface of the Earth. So that's the radial integration of the mode sensitivity, or these capital Ks, with variations in shear wave speed, P wave speed, and density. So what I'm doing is I'm saying, okay, at this point, what is the shear wave variation at all the depths? I'm going to weight that with how the mode is looking at it. I'm integrating that. Plus, I'll add the P wave speed variation and density variations. Just as before, the various modes would look at the inside of the Earth in a different way. So the capital Ks in here, sensitivity to shear wave speed, P wave speed, and density, would be different from mode to mode. For example, this mode from the surface to the center of the Earth is looking at the Earth in this way. It's very sensitive to P wave speed variations in the outer core. It's also sensitive to S wave speed variation in the mantle. It also has the sensitivity to variations in density, which is in green.
Is this splitting function calculated for one single observation or multiple observations?
So the question was, is the splitting function calculated from a single observation, meaning one earthquake or one station?
Either.
Okay, from a single observation or multiple observations. In order to create this splitting function, we need to have a lot of observations, so multiple earthquakes and multiple stations. So the answer is no, it's from a lot of observations. Any other questions?
Variation between either between stations or one event or between two different.
In order to create, so the question was, do we have a lot of variation from station to station when we are trying to make this splitting function? Is that the question. The fact is, this is all the stations contribute to making the splitting functions. So, not quite sure if I understand what you mean by variation from station to station. They contribute. It's an inverse problem, actually. So what you have is you have the observations, and you try to come up with this solution by fitting all the stations. Does that answer your question? Maybe, maybe not. Maybe we can talk later. Or the splitting is for all the stations. It's a single solution for everything. In other words, it's like one three-dimensional model is for all the P-wave observations and S-wave observations because they contributed in making that P-wave model or S-wave model. It's like that. This is an inverse solution from all the observations. So different modes look at the Earth interior differently. So here's the comparison of mode 1s4, which is primarily a mantle mode, meaning that it is sensitive to mantle variations. And this is the core mode. It's also sensitive to the core. So you can see that these modes have various different sensitivities to the various layers of the Earth. So if I combine multiple observations, so this is splitting function for 1s4, splitting functions for 6s3. If I combine all those, I would get some sort of depth resolution. Really?
The relative amplitudes of the two modes that are shown, are they correct? So it's the 6s3 has the same amplitude roughly as 1s4.
So the question is, are the relative amplitudes plotted here and there correct? In other words, are they comparable? The answer is no. I've normalized it so that you can see things well. But the relative amplitudes within a given mode is correct in that the S-wave sensitivity is much greater than density sensitivity.
How is the sensitivity kernel computed?
The question was, how was the sensitivity kernel computed? If you want to know the details, we start with the momentum equation, do the perturbation theory, and so on and so forth. The short answer is that you take the eigenfunctions of each mode and then do the perturbation theory to find out if you have a lateral variation, how would the mode see the interior? That would be the short answer question. Long answer question is you can read Dahlin and Trump 1998. It's this thick, it's heavy. But we can talk more about it later. Any other questions? So if you do that, so that's another inverse problem, right? Your data are going to be splitting functions, and your models, that the things you want to get out, are the three-dimensional interior models of S-wave speed, this red one, P-wave speed, and density. So here's S-wave variation as a function of depth. So here is 100-kilometer slice map view, blue being faster than average, red being slower than average speed. And then at 600, 1300, 1800, 2300, 2850. So this is very close to the Core-Mantle boundary. This is near the surface. Okay? So that's the S-wave speed. And the strength, I've again normalized these maps so that you can see the lateral variation well. But the scales are here. So you can see that the strengths are weakening in the mid-mantle and then picking up later as you go closer to the Core-Mantle boundary. We can also do this for P-waves. So again, P-waves from near the surface to the center of the Earth, and the density. Okay? In the case of density, blue is heavier than average, red is lighter than average, and you have the perturbations again. Now, with the modes, what I can also do is the fact that S-wave speed is simply rigidity divided by density, and P-wave speed is bulk modulus, shear modulus divided by density. Now, I also have the density, so I have three equations for three unknowns, and I can solve also for the seismic parameter squared, or the bulk sound speed, and I can solve for those. So here on this column is the plot of the bulk sound speed that I get from the mode inversion. This is the shear modulus or rigidity variation. So blue is higher, red is lower. On the right is the bulk modulus or incompressibility. And I can get these three sort of models. These are three-dimensional models. And the interesting bit happens near the Core-Mantle boundary, so I'm going to focus on that. If I look at the shear wave speed, P wave speed, and density variations, I have this. Now, again, these colors are normalized with these values. What you see is this red blobs underneath Africa and underneath Pacific. Those are presumably related to the LLSVPs. But density, you notice that they tend to have higher than average. Now, this doesn't change if you look at it in terms of rigidity, elastic moduli, so shear modulus, bulk modulus, and density. It turns out that the shear modulus is highly anti-correlated with bulk modulus, and this is the reason for a weak P wave speed. You remember the K and mu are added in order to make P, and therefore they kind of cancel out to produce this weaker lateral variation. Mu, again, these super LLSVPs are again anti-correlated with density. So what we see is strong anti-correlation between shear modulus and bulk modulus that leads to small amplitude of the P wave variations. And you also see density decorrelation. If you calculate correlation between this and that, it's fairly low. But if you look at the regional correlation, there is a strong anti-correlation at the places where you observe low shear wave speeds. So what does that mean in terms of dynamic? If I have low shear wave speed, and if I go ahead and be bold and interpret that as a temperature, I should expect lighter than average density, right? If I heat something up, the density should decrease. What I'm seeing is that when the temperature is high, the density seems to be also high. That could happen in, if you've ever played around with a lava lamp. This is higher than average density material that's sitting at the bottom. So even though this is heating up, you could still have something denser sitting at the bottom. And this would also explain certain observations. So for example, the seismologists observed that the boundaries of these big provinces can be very sharp. Now, that sharpness will be easily explained if you have a compositional variation. So you have a compositional domain associated with LLSVP and then ambient mantle. And then this boundary, the vertical boundary between those two provinces, could be sharp. And this is one example where they argue that there is a sharp boundary here between a low shear velocity anomaly. You could also play around with numerical calculations and put in a heavy material at the base to begin with and see how that evolves. And it gets swept around with the slabs subducting and plumes going up. And very often you end up with these heavy materials sitting at the location where you have high temperature. So it might be, if you look in cross-section, you have these dome-like features. And in experiments, you can also recreate that sort of feature. This is a tank experiment where you have this dome of heavier than ambient material with little plumes shooting up from the top. So what are the implications? What can we do with this sort of thing? I've argued that this might be related to composition by waving my hands. It could be possible. But what we'd like to do is convert these map or any other map you get from seismic tomography to variations that are more intuitive. Okay. So if I know the dependence of shear wave speed, P wave speed, and density to the parameter of interest, in other words, if I could get derivatives, how the shear wave variation depends upon variation in temperature, how the shear wave variation depends upon composition, same thing with P, same thing with density, I could convert the seismic tomography maps into models of temperature variations and compositional variations. I have the models, I have some observations, if you now call these observations. Now I'm going to use these sensitivity kernels to convert those into temperature and composition. And some people have done that. So here's an example. This is a plot showing the temperature variation, the amount of perovskite that's in there, and amount of iron. So in the composition or X field, they put in perovskite and iron. So you could put as many composition as you want if you have those values. And inverted for these fields, for the upper part of the lower mantle, 670 to 1200, middle part, 1200 to 2000, and then the bottom of the mantle. And they can get this sort of variation in temperature, perovskite, and iron. And that might be more relevant if you're interested in what sort of material is sitting there or what sort of dynamics we have. Now, the problem is we need the robust constraints on dependence at high temperature and pressure. We are dealing with material at high temperature and pressures. So these derivatives need to come from a condition corresponding to the Earth's deep interior. And that is, as I understand it, difficult. So it's something for mineral physicists or experimentalists, theoretical and experimentalists, to give us, and we can work out what sort of temperature and composition variations we have. Any questions before I go on to trash all the mode models?
You only use normal modes for these. Why not include also the body waves, constraints, and velocities?
So the question was, I only used the normal mode for this construction. Why don't I use the gravity? Why don't I use the seismic wave speed observations? One reason, I could. What we have tried is we've actually iterated this isn't, what I'm showing is different, but what we've tried is we've iterated between body wave inversion and normal mode inversion to come up with a model that's consistent with one another. I could just throw in the body wave information into the inversion to constrain the SNP models better. But you might see some of the reasons why we don't do that in the next bit of discussion.
You presented this as a fact, but I think it would be important to point out that these density models are controversial.
So Barbara's point is that these density models are controversial, and that's where I'm going to get to next.
Let me ask you a naive mineral physics question, which is, when I actually look at your images right from 2 slides ago, I'm guessing, it looks like there's an offset to me between the density anomaly and the shear velocity anomaly, probably 2,000 kilometers or so. Should I believe that or not?
So the question was, if you look at the density versus the other parameter comparison, there seems to be a bit of offset between this blue blob and the red blob and this blue blob and the red blob. It comes from the fact that the density, being a little technical, density has a very strong degree 4 structure, whereas these guys have strong degree 2. And if you look at the density degree 2, there is still strong decorrelation or anti-correlation around here. So it's partly have to do with the fact that I have higher spatial structure in density than in the shear. Is that a real feature? I'm not sure. But if you focus on degree 2, you can still see the anti-correlation in there. There was another question? So the question was, how does the anisotropy affect the inversion of the normal modes? It will affect it. So for the time being, we've ignored it in this calculation. But if you think that there is strong anisotropy in here, the modes would definitely get split by the presence of anisotropy, and you should include it. We haven't investigated that effect. So the question was, what is the vertical resolution of these maps, which is what I'm going to get to next. So if you could hold off on that a bit.
As you point out, the density has a more power in degree 4. But I've always been struck by how strong the dominance of degree 2 is in the seismic process. Do you think that's a significant? You use the word decorrelation a lot, because I don't think anti-correlation is convincing when you have different degrees. But do you think there's something profound in density having kind of a different heterogeneity distribution?
So the question was, most of the seismic models, seismic wave speed models, have very strong degree 2 structure, which you'll see next. So do I believe the fact that the density has a smaller scale, higher degree sort of structure? Did I summarize it reasonably well? Okay. I've wondered about it, so that's why I've looked at just degree 2 component of this. And because I still see the difference in the degree 2. That's why we came up with this conclusion. Whether the degree 4 is good, degree 4 is robust, I think there are enough observations to constrain it, but as I'll get into, there are trade-offs and things. So there are a lot of uncertainties in there. Any other questions? So that's all nice and great, but as people pointed out, there are certain problems and certain advantages. So let me talk a little bit about pros and cons of looking at things from a mode perspective. Now, if you use normal modes, you don't really have to worry too much about the sampling bias. If you look at the surface wave coverage, in other words, where am I sampling in the Earth, turns out you're not going to get global coverage. This is a coverage plot, meaning that dark colors are places where we are sampling well, and light colors is where we are not sampling too well for the surface waves. Modes, you're basically dealing with the global sort of motion, and therefore you don't have to worry about it too much. There is a little bit in there that you do have to worry about that I'm not going to get into. So that's one advantage. There are problems, though. The sensitivity to density is not as strong as sensitivity to other things. So in this particular mode, 1s4, which I showed you before, the red is sensitive to S, blue is sensitive to T, and green is sensitive to density. Now, the relative amplitudes is correct, and therefore you'd infer that the sensitivity to density is limited. And because you're dealing with elastic variations and you're going to get into higher frequencies where the gravitational restoring force is not going to be as important, you're going to lose sensitivity to density. The other problem that I'm going to get into a little bit more is that you have to obtain models of S, P, and density at the same time. In other words, you're going to introduce certain problems there. You're also going to have poor resolution in depth. Right? This is fairly broad, and I'm integrating over with that broad kernel. In other words, I'm not sure if that effect is coming from here or there or there. We are also limited to large-scale structure. Remember, the entire Earth is moving, and the way we see it is the entire Earth. In other words, we are not going to see small-scale structures. I'm going to illustrate this problem with using a tomographic model. Here's one tomographic model at shallow surface, shallow depth. So you see the ridges and continental material. Now, this looks familiar, but the scale we are looking at with MOSE would look like this. So the fine features of the ocean ridges would disappear. It would become very smeared out, blobby features. So all we can do in terms of mode inversion is to look at large-scale structure.
What spherical order are you using in the lower?
So the question is, what is the spherical order am I using in here?
Yes.
In the mode modeling? It's up to degree 6, and this gets worse.
Did you include the odd?
I'll get to that. Okay. The other problem, the fortunate bit about the large-scale structure is that the Earth interior seems to be, especially in the lower mantle, dominated by large-scale structures. So this is power spectrum as a function of depth at different angular degrees. Consider angular degrees as small-scale features as you go to high numbers and large-scale features as you go to low numbers. So in the lower mantle, from this line below, you have a lot of power at degree 2 and 3, in other words, at this end. And so the fact that we are limited to large-scale features might not be too bad. But there is another problem. The mode data, the way the data set that I'm using, or we are typically using, are only sensitive to even degree structure. So this is simply taking this model and then making it down to degree 6 or large-scale structure we are seeing. But if I remove the odd degrees, what we will be looking at would look like this. So what we can constrain is more or less symmetric structure. So from here, we've gone down to here, which would make it very difficult to interpret if you want to interpret with respect to surface tectonics and such. So we've now, this red feature has become a lot larger and blobbier than here. This lost a bit of some of the legs here, and so on and so forth. Now, why is it that we are limited to this symmetric structure? It comes from the fact that the modes are simply standing waves on the Earth. So the standing waves in physics lectures, you've seen these sorts of things, that these are oscillating features. And depending upon the boundary condition, in this case, fixed boundaries, you can only have sine-like behavior. I can't have a cosine, because then I would have a problem down here. You would have higher orders, first order, and second order, and so on and so forth. But they'll always have to be pinned at the ends. On the Earth, we have a similar problem. You can think of the normal modes as the standing waves. In other words, the waves, let's say surface waves, going around and around the Earth, interfering constructively and destructively to produce a mode or standing wave. So if you have an earthquake, Rayleigh waves or surface waves propagating around and around, which is what these guys are, so we can actually see them, they would have to constructively interfere in order to make this sort of standing wave. In other words, I'm not going to have the cosine part from the previous illustration, which corresponds to the odd degree or non-symmetric structure sensitivity. And that's why we only end up with the even degree structure. Okay, so it doesn't look great, but at least we can get to this point. The other problem with modes is that it requires giant earthquakes. Magnitude 4 isn't big enough, right? So if we look at the last 100 plus years, here's the list of giant earthquakes with magnitude greater than 8.5. This is it. Right? And in the last, well, since the CIDER's inception, we had so many of the giant earthquakes. But before that, the biggest one is this 1965 Rat Island, which is basically analog data and hard to work with. You can get around this a little bit by reducing the magnitude and trying to see certain modes. But we would definitely want to have this sort of giant earthquakes in order to work with modes. So what sort of things should we be careful when we are interpreting mode data? Well, the poor depth resolution. So if we ask the question of, okay, I have a structure at 1,500 kilometers depth in shear wave, what does that mean? Well, it gets broadened out. So it could come from anywhere from here to there, 1,300 kilometers. If I have something in P wave at that depth, it again gets broadened out. Density is the same thing. So even though I see a density variation at a given depth, that is probably some depth integrated expression around that depth. The other problem that you can see in this sort of plot is the trade-off with various things. So even though I only have the shear wave variation at 1,300 kilometers, it would go into density variation, which is the green curve, and then also P wave variation. So there is a trade-off between the seismic wave speeds and density variations, which we have to be a little careful of. This perturbation variations or trade-off would vary as a function of depth. So if I put something at 1,300, it would look like this. If I put something, if I'm interested in near core-mantle boundary structure, it would look slightly better in that they are more isolated and not a lot of trade-off happens between shear and the density or P wave. P is, again, more isolated. Density is more isolated. So you do this sort of test to see where you would feel comfortable interpreting the data. But there's definitely problems in just taking the mode or any models and say, OK, I know that exactly right there. I have the same problem when we are looking at the PREM density structure. Mineral physicists tend to ask me, what is the error bar on the PREM density? I don't like to say it's plus or minus 3%, say, because if they fit the PREM density profile with, let's say, plus 1% throughout the mantle, It's fine from the fact of saying plus or minus 3%, but it has a significant problem because you're not going to fit the mass of the Earth, which we know quite well. So in any inverse problems, be careful with what you're looking at and try to understand what sort of constraint and broadening and trade-off you have. And just relying upon the uncertainty estimate might not be a good way to go forward. Any questions? So the modes also give you, the only way I know that seismologists can give you viscosity, and which is through this Lichter mode. This is a completely different mode from what I've been talking about. This is an exotic mode, which is inside basically the motion inside the outer core. So here's the outer core. We have the solid inner core. And the solid inner core could move sideways, displacing the outer core. Now, if this mode exists, theoretically it does, it's a translational inner core mode. So the outer core stays put. It doesn't move. But the inner core moves inside the outer core. And it's called Lichter mode. You might be able to observe this on a superconducting gravimeter because they are fairly sensitive at the lowest frequencies we want to get to. It is going to be sensitive to viscosity of the liquid outer core because what you're doing is you're displacing the outer core by moving the inner core sideways or up and down and so on and so forth. So this predicted period would have some sort of sensitivity to viscosity. So if you change the viscosity of the outer core, this value would change. So the question was, what's the magnitude of the motion? I'll get to it. So hold on. You had another question?
What's the nomenclature? What's the labeling of it?
Lichter mode?
Yeah, 0, something 0.
It's 1s1. Thank you. 1s1. No, I don't think it's quite 1s1, but it's similar to it, I think. So the problem with Lichter mode in terms of what's the amplitude, it's hard to excite this mode, right? You have to keep the outer core stationary and just move the inner core. There's, as far as I know, there are no earthquakes in the inner core, which would definitely excite this type of motion. So people have looked for it. But you're dealing with this sort of data set. So here's amplitude versus frequency again. Now we are in the range of 10 to the minus 5. And so we are really, really low frequency. The predicted Lichter modes from PREM with certain viscosity is here from the Dahlin and Seller paper. There are a bunch of claims of seeing these Lichter modes that are sitting here. These Lichter modes come in threes, and that's why they have these 3 arrows. So one is here, one is there, and there are additional observations. It's hard to find 3 peaks in here. On top of that, you're looking at something around 6 hours. In other words, you're starting to interfere. Your data is going to include things like the tide up here. So these vertical lines are various tides, forced oscillations of the Earth, and you see that the Lichter modes could be very well hidden in that information. So it has been very hard to find them, and I don't think there is a convincing observation of that.
Why are there 3 Lichter modes? Is it the shape of the core?
Lichter mode is degree 1. So if you split it, you have m is equals to minus 1, 0, and 1. Any other questions? So it's the Zeeman splitting bit. Okay. So, let me get through the attenuation very quickly. So another thing you can do with modes is you could look at the attenuation. So if you have the sinusoidal wave, we feel the earthquake, but we don't feel it forever. In other words, the waves would decay out, right? The ground shaking don't last forever. And you can write the sinusoidal wave, the displacement, as a function of amplitude, initial amplitude, the oscillating bit, and the decaying bit. And the value Q, as Steve defined, gives you this decay as a function of time. And the Q inverse is related to the amount of energy you lose per cycle compared to how much energy you started out with. Okay. So the top bit is the amount of energy dissipated, bottom is where you start, and this Q is called the quality factor. And it's very important that you have a capital Q. So this is basically damped harmonic oscillator. So if I take this sort of signal and Fourier transform it, I get a peak with certain width. This width is directly associated with this Q value, how fast or slowly you're decaying. If your decay is very slow, your peak is going to be sharp, so the width will be small. If you're decaying very quickly, your width is going to be wide. So what we could do is we could look at these peaks and try to find how quickly or how wide or how sharp it is. So 0S0 looks very sharp compared to some other modes. Now, the problem is we saw that this includes splitting associated with the rotation, ellipticity, and variation, lateral variation. So you have to correct for that first before measuring the width of the mode, except for the radial modes. But you can do that. And if you look at 0S0, this is the number we had before, 2077 hours. That's associated with how long it takes for that mode to lose E of energy. So that's actually associated with attenuation. Same thing with 0S2. It takes fairly long time to lose energy. Now, if you don't want to deal with the fact that you have the splitting of the mode, the other way to look at attenuation from the mode perspective is actually look at how the modes decay. So here is a spectrogram from the magnitude 9 Japan earthquake on the vertical component. So what you're looking at are these spheroidal modes, the ones that are associated with the deformation of shape. Now I'm going from 0 frequency to 3 millihertz. So you see more peaks than you did before. What I can do is I could take certain length, create this spectrogram, move to another time window and create it, and do that for a long time. And I can make a color map. So the color is showing you the amplitude of these peaks from time close to the event time down to 950 hours or so after the earthquake. In other words, this would give you about 40 days after the event. So you can see that the modes are excited. They are clearly seen at the beginning, but they decay out. This one lasts forever. This is 0S0, the one with the very narrow peak. So this is associated with very slowly decaying mode, whereas some others up here would decay immediately, giving you the Q value or attenuation value associated with the mode. And so you can see that those Q values would have various lifetime of the mode, and you can measure it this way or through the width of the peaks. Thank you for asking. I was hoping that someone would ask. What are these red peaks that pop up? These are actually aftershocks. Okay, so the PREM actually has attenuation. Oops.
Do you expect more splitting in the slow decaying modes? Do those split more times when you look at the wiggles on like the top amplitude chart?
The splitting is not really depend upon how quickly or how slowly they decay. They depend upon the rotation, ellipticity, and the internal structure. Any other questions? So the PREM model does have a Q value, and it's very important that it does it because of the fact that Steve talked about yesterday. The elastic or wave speed, elastic variables depend upon frequency if you have attenuation. In other words, even though Q might be constant in the seismic frequency band, the wave speeds could be changing. This is just a cartoon, don't worry about the axis. As a function of frequency, the wave speeds could be high if you're high frequency and low if you're low frequency. And when I'm doing normal mode calculation, I actually have to tweak the PREM model to fit to the frequency of the mode I'm looking in order to make it work. So just give you an illustration of how important it is. This is the expression I'm going to use for the shear modulus and see how much of a sensitivity it has. If I start with the reference frequency of 1 Hertz, so that's what I'm going to plug into this angular frequency omega naught. Take a shear wave speed of 4.5 kilometers, density of 3.4, Q mu of 80, which is pretty low. I would get the mu value of about 7 times 10 to the 10 pascals. Now, I'm going to look at the effect of the Q in this sort of range. So body wave range, surface wave, normal modes, as a function of period or frequency. At the 1 Hertz, I have the reference value, which is this guy here. But if I go to lower frequency, 0.01, that value would change to 6.84. If I go to normal mode sort of level, it's 6.8. So that becomes significant when you're trying to fit the data. If you go to deformation at a longer time scale, the mu, even though you're looking at the same thing, same material, would be 6.71. If you go to higher values, it would increase. So the problem here is that mineral physicists would give us values of shear and bulk modulus, but it's not quite clear to me how we should compare those.
I just want to make the point that the correction that you made from 1 to 1,000 hertz assumes that the absorption band continues from 1 to 1,000 hertz. Whereas we think, I guess, in the Earth, maybe I'm mistaken, but in the Earth, the corner is thought to be somewhere between 1 and 10 hertz, right?
So the comment is that this is assuming that the Q is constant throughout the frequencies I'm looking at here. And Ved is making a comment that it would have somewhere a corner. As far as I know, the location of the corner frequency isn't quite clear. There are some arguments that it would happen somewhere between here. I've seen some arguments that it should extend to about 1,000. At the lower end, in terms of the tidal forcing, we don't really see a strong difference from the Q value inferred from seismology. So I'm not quite sure personally where that corner is.
But on the high frequency and I think from body wave studies, we have a pretty good idea that it's around 1 second. I mean, it's not.
I've seen a paper or two with 10 and 10 seconds or so, but
yeah, I'll talk about that tomorrow. That we're trying to put it into a context where we think it comes from on a grade scale basis and talk about the absorption band in that context.
okay, so Willie's making a point that he'll clarify all this to you tomorrow.
Miaki, over here. So another quick comment for people who aren't familiar with the PREM paper. Everybody should read that PREM paper, maybe only ever once, but everybody should read it. It actually tabulates the PREM model at 1 Hertz, the reference frequency, and then there are tables in that paper for what that would look like at 200 seconds. So if you look in the paper, you can actually not have to do for yourself this calculation that Miaki has shown you. You can see the effect line by line in what the model would be like. So that's actually one of the many kind of gems sitting in that PREM paper that Miyaki's been talking about today.
So PREM, as mentioned, is at 1 Hertz. So if you're looking to compare it at different frequencies, you might want to consider the dispersion effect. Now, the last point I wanted to make is that we don't know where that frequency independence of Q comes from. So if you look at the physical mechanisms of energy dissipation, you don't really get a flat thing as a function of frequency. So this is frequency going from 10 to the minus 14 to 10 to the 5, and there are different mechanisms. There is the pair of solute atoms, grain boundary effect, twin boundaries, and so on and so forth. They don't look anywhere flat as a function of frequency. But the seismologists would talk about flat sort of Q value based upon various observations. And we've said, okay, that's roughly constant Q over seismic frequency band. We've also waved our hands and said we can make a flat Q even if we start with the Gaussian sort of distribution, if I add a lot of those in a right way so that we can come up with the sum of the frequency content, frequency dependence, that ends up being flat. So one of the things I was talking with my mineral physics colleagues was how to go from this state to there. Or is it that the seismologists would have some limited sampling at various frequencies that we are actually not looking at a constant Q, but some bumps here and there that we just don't have sensitivity to? And I don't know the answer to that question. So the comment is that the right figure is the Q, but it's not necessarily directly comparable to this because very oftentimes the Q measurement has to rely upon the measurement of amplitude. And that's, again, something very difficult. You might have this structural effect, defocusing and defocusing, and so on and so forth. I agree with you, but although people do convert this to a Q intrinsic Q value, and that's one of the reasons why I prefer to do it from the normal mode perspective. I don't have to worry it as much as if I'm looking at the body waves.
I guess this is another comment. This frequency dependence of Q is something that is a topic of obviously active research, and there are a number of studies, some looking at body waves, some looking at normal modes, which do obtain a non-constant Q in the seismic frequency band, so an alpha of about 0.2, 0.3. Which now I'm going to, I guess, echo what Shinkarat always tells me, which is you should have 0.3 because every material we look at looks like it has 0.3. So it's just something for the young ones to try.
So the comment is that it's not not everyone agrees this should be flat. There might be some curve to it. But I would still make the argument if you look at these microscopic mechanisms, we don't get a curved line. Right. So we would have to go from here to flat or linear or whatever model, but that's something that we are. Okay. Well, then I'm done. Thank you.
Okay, Lily's going to talk.
So one question I had, so going back to the Bullen parameter, if you include attenuation and also, so your P and S wave observations are made at different frequencies, and if you go back to the Bullen parameter and take attenuation into account, would that modify? Because attenuation is not in there intrinsically.
The Bullen's parameter I calculated from PREM, so that's at 1 hertz.
Right. Yeah.
So the question was, is the Bullen's parameter going to be different if I include attenuation because the P and S have different frequencies? The frequencies that I have is from PREM and therefore 1 hertz.
So corrected with one of these approaches, right? You have to correct from the frequency at which you make the observation to 1 hertz. So then it depends on what kind of correction you use to 1 hertz, whether you use constant frequency dependence or frequency dependent.
I suppose that would be the case. I'm not quite sure what the effect of this dispersion is going to be on the Bullen's parameter, and I'm not quite sure what frequency I should be calculating Bullen's parameter. I mean, it will be very, very long, low frequency sort of effect if you want to relate that to convection. And so we'll be lowering the wave speed significantly. And again, that comes down to where is the corner.
There is a little differential effect on P velocity versus S velocity. So when computing the Bullen parameter, there would be a small frequency dependent shift. The S is more effective on it.
So in everything that you showed, the one thing that I found really disturbing was when you took the seismological model and then showed us what it looked like with the normal modes and the effect of having only the even values, because you end up shifting like features, like there was the blue Bullen side that shifts like 1,000 And so how do we go about interpreting it, right? Because it means that you can't just, like if I opened up one of your figures and looked at the paper, I couldn't look at that and say there's a higher rigidity thing here, because it might be over here. So what's the best way to go forward for people who are trying to connect what you're measuring with the normal modes to where the features are and what features are actually, what are you actually seeing with those in terms of 3D structure?
So the question was, the fact that the normal modes are sensitive to the even degree structure makes it very difficult to interpret in terms of the actual location, because the features might be shifted and so on and so forth. The way I look at it is in terms of comparison between models. So how the shear and P wave speed are correlated, or shear and density are correlated. And so one of the things we've done is to calculate the scaling relationship between density and shear wave speed, which is often used in the dynamic calculations when you if you invoke the Mantle flow and take the shear wave model and then make a density from a scaling. So that sort of thing we can definitely do.
Just extracting that information without worrying about exactly the location of where it is.
Right, so bringing out the relationship between the models rather than worrying about what exactly is at this particular location.
So what happens if you take like a whole seismic model, somebody else's body wave model, and then express it in terms of just the even modes that you're able to see? Do you see features that are in the same location? Is that consistent?
So the question is, what happens if I take a model, seismic tomography model, that has both even and odd, and express it in terms of even and odd degrees? So here's the comparison with the shear wave model. Taken to the same degree, so just the even degrees, and left is the mode model, right is the body wave model. So for S, and the scaling and so on and so forth, this is comparison between P, and I obviously don't have a density, but you can see that these correspond reasonably well. One of the reasons, though, is that we do have models as the starting model. So that's one potential problem in seeing similarities. But if you take a starting model out of the inversion, you could still get something looking very similar.
So do we have any student questions before the exam on normal modes?
It's hard, right? You're ready for lunch.
All right, we got one.
So last question, because it's lunchtime and maybe out of the scope of this talk. But when you were talking about the Schlichter mode of the inner core translation, you mentioned how it was dependent upon the viscosity of the outer core. I wonder also if anybody's done the calculations for, you will drive flow around the inner core, which will shear the magnetic field as well. So I would imagine that because the magnetic diffusivity is so much higher than the physical viscosity, that it would also be highly dependent on the magnetic field strength. Is that true, or am I just in the wrong order of magnitude?
I think Tanimoto has looked at that sort of thing, flow in the outer core and how much of the mode can be affected, and it was tiny. That he concluded that it's negligible, it's within the noise that we can't see.
Okay, let's thank Miaki again. We'll break for lunch.